about refraction. Refraction. So after reflection, now comes refraction. The difference between reflection and refraction is this. In reflection, the waves or rays, they bounce back into the same medium. Whereas in refraction, it's going from one medium to another. Okay, it's crossing over and going to the other. So that's the main difference. When a ray or a wave goes from one medium to another medium, then we call it refraction. And what is going to really change is this. Like, if I look at this as a surface separating the two medium, let me call this air and let me call this glass. Now, glass is optically more dense than air. Now, that's what we call as optical density, and you'll learn about it later on. So what is this optical density? Is it a real density, mass density? No, mass density is totally different, mass over volume. But optical density is how are the waves affected upon entry into this thing? That is what optical density is. Okay? So optically more dense. So air and glass. What happens if waves are going to come in like this? These are waves. So waves are going to come in this direction. The waves will enter the medium, and once the wave enters the medium, now remember, you know these waves, each is a wave front, and the wave front is constructed by, each wave front is constructed from miniature waves coming from there. So like tiny waves all put together, the tangent of all the wave fronts edges gives you the new wave front. Okay? So these are all wavefronts coming in. What's the space between one wavefront and the other? Wavelength. Good. So that's the wavelength. Now what happens when a wave goes from an optically rarer medium? This is rarer and that is denser. So from an optically rarer medium, if it's going into a denser medium, it is going to be affected in speed. Okay? Think of you walking on a normal ground and then step into sand, or keep walking in sand. So when you're walking normally, you keep walking on the normal road, and then once the sand comes, you keep walking, right? What is changed as you keep walking? Number one, as you keep walking, your speed is changed, right? What else changes along with that?
Size of your steps.
Size of your steps, which is basically referring to the wavelength. So when you're walking, that's your wave length, your left and right. Now, what happens to the frequency?
Increases.
The frequency of your steps.
Decreases.
The frequency of your steps depends on your leg's length. It's a characteristics of your body, and that's not going to change. The number of times you're going to flip your legs left and right will not change. Make sense? The frequency of light will never change. Frequency stays the same. So what changes is velocity and correspondingly the wavelength. So what happens as this goes inside, it's going to slow down. And so these are the waves. The wavefronts are now like that. What do you see here? Different from here. Shorter wavelength. So this wavelength is now shorter. And that wavelength is bigger. And why is this shorter? Because it's slower here. Right? So the speed here is lower. And you know this equation V is equal to F lambda? F stays the same. So when the V changes to V prime, lambda changes to lambda prime. So the speed is the controlling factor there. So when the speed changes, immediately the wavelength is going to change. So what you saw right now is when the waves are going to enter like that, they will slow down as it enters the medium. And as it slows down from one medium to the other medium, light when it's going, now we are generally extending it to light because we're talking about light now. This applies to all waves, sound waves, anything, mechanical waves, anything, right? So this is now we are referring to light. So we're talking about speed of light in air and speed of light in glass. So if you're comparing the speed of light in air and glass. So in glass, the speed of light is affected. And that is why it's traveling slower. It is going slower here. And because it's going slower, the wavelength is affected. Is that clear? So what is refraction? What is refraction? Now, some books word refraction in a wrong manner. They define refraction as bending of waves. Bending of waves as it enters into a different medium. But is it really bending here? Do you see bending here? No, it just enters and goes straight. So even this book says that. Let's see. This one says the ray changes in direction as it enters a new medium. This change in direction or bending is called refraction. This change in direction is called refraction. That is refraction. So basically what is refraction? When a wave goes from one medium to another medium, the speed is affected, and that is refraction. Okay? When a wave goes from one medium to another medium, automatically it is refraction. It's refracting into the next medium. But that refraction can cause bending. It can cause bending. Now think of the example that I mentioned last year when we were talking about waves. Wheel and axle. Think of wheel and axle. Suppose you have, this is sand, and that is proper floor. And then if you have two wheels and connected to an axle, and if I roll this thing straight into sand, so the wheel and axle, they're going to come like that. Both the wheels are going to enter the sand together. So both wheels will actually be slowed down together. So they'll be going together like that. Make sense? Now think of the same thing coming at an angle. The wheel and axle are coming like that. This wheel is going to touch first, and so will get slowed down. Think of it more practically. This will get slowed down. That is still moving. So what will it cause? A turning effect. Which way? After coming like this, which way is going to turn? Like that or like this? Right? So it's after this is turned around, it goes like that. So it comes from here and goes like this. So the wheel and axle is going to get bent. So here you don't see any bending because the angle of incidence is 0. It comes right through. But here it's coming at an oblique angle of incidence. And that is the reason why you see a bending. So bending is a possible consequence of refraction, especially when it's coming at an angle. Make sense? So let's go into that a little more in detail. So when the waves come like this, you don't see any bending, but it is refraction because there is definitely
So like when the waves come through, like, and they go from the rare medium to the denser medium, and then the wavelengths get closer together.
Mm-hmm.
What would an observer see? Or how would that change the image? Like if the wavelengths are closer,
the wavelength changes. The wavelength is the color of the light, right? If you're looking at the color of the light, the color is supposed to be different inside. But you are outside. You're not inside the medium. Since you're outside, you still see the same color. Got the point? That's a good question. Suppose it's going as red. When it comes here, it is actually lower than red. Okay? Like, oh, orange. Okay? So if this is red coming in, it may turn into an orange color. But it's orange color in the medium. But since you're outside the medium, it will change back to red again when it comes to your eyes. Make sense? Unless your eye is kind of glued inside the medium itself, then you may see a different color.
So like if the waves are coming at like a straight angle into a medium, and then you're on like the outside of the medium looking from the other side, will there be any refraction?
Like for example, if suppose this is going back to air, it will go back to the same thing. Make sense?
So you won't see any refraction like through that. Like
No,
in this
you will-
example, like,
No, in this case, what's the refraction again?
it's from like if waves go from one medium to another,
Speed
medium, it
changes.
changes speed.
Speed changes cannot be noticed that easily with your eyes. What you can see is the angle changes. That's why most people actually tend to call refraction as the bending. But bending is not a must. You can have a ray of light going straight through. Depends on how it's entering. That's why I give this example. So if it's going straight through, it will not bend. It goes straight. But if it is coming at an oblique angle like this, then bending is a possible consequence. Yeah.
So you know how your eye is filled with fluid?
Mhm.
Well then, does that mean that like all the colors we perceive aren't the colors?
Actually, yes. They're all kind of, it's a lot of factors. That's also another point. So when your eye, your lens is actually refracting, you see? It's refracting inside. The perception of what you're actually seeing is not exactly what is happening outside. So once it enters into that fluid and then goes to your optic nerves, and then your optic nerves will pick up the signal, right? So all those things are actually different. Now, what we are considering to be the wavelength are the wavelengths that are measured by instruments. Say, if I send light into an instrument and that instrument measures the wavelength, we'll see later on how wavelengths can be measured. Okay, you can measure them. That's what we are looking at. Now, when you look at a certain color, the aspect of internal refractions and changes of colors, wavelengths, all those things can happen, but then our perceptions are all based on that.
So what if someone's optical density was different? Like the fluid?
So the fluid inside there, it's normally the same. I mean, if there are slight differences, perceptions could also be different.
Like how much of a difference would it take, like in your eyes, for it, like for colors to be perceived completely differently? Like the difference in.
Oh, that should be a lot. I mean, like, it's almost like somebody has no fluid at all to fluid inside. Yeah, we'll see more and more about it. We'll see more and more about it. All right, now let's go carefully into the refraction. You draw that diagram properly. That's more important. And now, let's look at waves coming at an angle. So these are waves coming. Let me draw the guidelines for this. Okay, sort of. Now this is a wave front, and these are all wave fronts. Those are all wave fronts coming in from an angle. You see? So let's say AB. AB is the incident wavefront. Go ahead, write it down. Draw this diagram, very important. That's the wavefront, which is the incident wavefront. Okay? Incident wavefront. AB is the incident wavefront. What's the gap between here and here? Wavelength. Now we are looking at air to glass. Let's take that as an example. So we're looking at the waves coming from air and moving into glass. And as I told you here, you know what each wavefront is made up of. Each wavefront is made up of miniature waves going from each and every point. From each and every point of any wavefront, there are miniature waves spreading out. And if you join the tangents of all the miniature waves, you get a straight line, which is a wavefront. Now, why are these wavefronts not bent? It is like straight. Because we are assuming that they are coming in a parallel manner. These are plane waves. Plane waves are wavefronts that come parallel. Now, you can have different kinds of wavefronts. Wavefronts that can be like that, right? You can have circular, you can have spherical wavefronts. Plane wavefronts are wavefronts that are coming like this, flat. And when will they become plane is when these are coming from a very distant place, like sunlight. The sun rays are coming from far away. So the wavefronts of the sunlight reaching us is nearly plane because of the distance. Okay? So these are plane waves. Now what's going to happen to these wavefronts as they enter? Which one touches first? Which edge touches first? A. So when A touches first, it is now going into a difficult medium. So it will automatically slow down. Whereas B is still moving in air. And so by the time B reaches C, A would have sent its waves some distance shorter than that. A would have sent waves into the medium, into glass, not too far away. Look at the distance, and look at this distance. So by the time B reaches C, A is in this area. Okay? So where are the others? Where are these midpoints and all that? They'll all be in between here. So how do you find out the wavefront? Emerging wavefront, this is what it is. I'm drawing a tangent to this curve. So this one is an emerging wavefront. So this is the emerging wavefront. So this is incident wavefront. This is refracted wavefront. Refracted wavefront. What happens here is that once they're both inside, let me call this D. Let me call this refracted wavefront CD or DC or whatever, this one. What happens to the once it's completely inside the glass, they should go together, right? So they're going together. As I asked you earlier, what's the significant difference you see inside the glass? The wavelength is different. This is lambda G. This is lambda A. Lambda G, the wavelength in glass. Lambda A, the wavelength in air. Obviously, lambda A is bigger than lambda G because it's going slower in glass. So how fast are these wavefronts moving here is, let me call it VA, which is the speed of light in air, which is normally written as C. C is the speed of light, okay? But I'm writing it as VA right now. So VA is the speed with which these waves are going down, and VG is the speed with which the refracted wavefronts are moving. What is the angle between a wavefront and the incident? Now, this line that you see here, that's an incident ray. You can see both models right here. I told you waves, the light can be studied with wave model and ray model. Here's a wave model. That's a wave model. This is the real thing, what's happening. But to make things easier, we need to look into incident ray. So this line that you see here is an incident ray. What is the angle between the incident ray and the wavefront? 90. Always supposed to be 90. Wavefront and the ray, they're always 90 degrees to each other. Okay? So this is 90 degree here. Which means this is also 90 degrees here. Now let's study more geometrically into it. On this diagram, do you see the incident angle of incidence? Angle of incidence. And what angle is coming and striking? Can you see it? Or where is it supposed? What is the angle of incidence by definition?
Where it meets the change of medium.
Yes, but with respect to what? All angles are measured from the normal, right? Even in mirrors, all angles are measured from the normal. So where's the normal here? This is our normal. That's our normal. So this is our normal. And this angle is the angle of incidence. So I'll call it theta A. I'll call it theta A. So that is theta A, angle of incidence. And where is the angle of refraction? Now this is the refracted ray. This what you see here is the refracted ray. Where is the angle of refraction? It is the angle between the refracted ray and normal. I said always all angles are with respect to the normal. So that is theta G. Let me call it theta G. Now, what do you see over here? There are two right angle triangles. You see that? AC is a common hypotenuse. AC is a common hypotenuse for this triangle and for this triangle. Now let's investigate a little further. That is theta A, right? What is this angle? What is this angle? 90 minus theta A. Remember, this is not a reflected ray. This is the incident wavefront. Okay, it may look like it's reflected, but no, that's not reflected ray. We're not showing reflection at all here. And if at all reflection is going to come in, it will be at the same angle as theta A, because angle of incidence, angle of reflection, right? But this is 90 minus theta A. That's 90 minus theta A. If this is 90 minus theta, what is this? What is this angle? Theta A? Because the angle between the normal and the surface is also 90. So this becomes 90 minus theta A, which is theta A. So in this right angle triangle, we understood that this angle also is supposed to be the angle of incidence. Similarly, what is this angle here? Theta G. What is this angle here? 90 minus theta G. That is 90 minus theta G. And if this angle is 90 and this is 90 minus theta G, what is this? This is 90 minus theta G and this is already 90. What is this one? Theta G. Okay, so complementary angles. These two are supposed to be complementary angles. So we get theta G right there. So now we have two right angle triangles with a lot of things known. So let's look at it more trigonometrically, because to connect angles to sides, right? So what is sine of theta A from the right angle triangle? What is sine of theta A. BC over AC. What is sine theta G? AD over AC. AC. That's the hypotenuse. So sine of theta G is opposite AD over AC is the hypotenuse. Now if I divide both these equations, what do you get? Sine theta A over sine theta G is equal to. If I divide both the equations, BC over AD, because you can see AC and AC is gone. AC and AC cancels off, BC over AD remains. Now let's go to that picture again. By the time B moves to C, do you get it? By the time B moves to C, A goes to D, which means the time it takes for B to C is T, so the time it takes for A to D is also T. So connecting these, can you tell me physically how much is this length BC? It's moving at this speed for this long. So BC is VA times T. And AD is VG times T. Now T and T cancels. So we have some interesting relationship there. That is sine of the angle in air over sine of the angle in glass is equal to the speed of the waves in A over the speed in glass. You also know this, that V is F lambda, right? Since V is F lambda, you can write this. Since V is F lambda, you can write VA as F times lambda A and VG as F times lambda G, lambda A, and F cancels. So what do you end up getting? Sine theta A to sine theta G is equal to VA to VG is equal to lambda A to lambda G. So when refraction takes place in an oblique manner, like as I've shown there, bending is going to take place, which means definitely you are talking about an angle of incidence and an angle of refraction, which is not there when it was going straight, right? So since there is an angle of incidence and angle of refraction, there is definitely a ratio that you can see. So these angles are connected to this ratio. So if these angles change, the ratio will still stay the same. This ratio is going to stay the same because the speed of light in air, this is the speed of light in glass. It's a constant ratio. So the sine of the angle on this side to the sine of the angle on this side always bears a constant ratio. And that constant ratio is called refractive index, sometimes also known as index of refraction. Refractive index of glass with respect to air. Refractive index of glass with respect to air. And I told you this is a constant number. It's a constant ratio. Refractive index of glass with respect to air is always a constant ratio. Refractive index of glass with respect to air is a constant ratio. Now this refractive index is symbolized by the letter mu or n. Some books use mu as a symbol. Some books use n as a symbol. Most books these days use n as a symbol. Mu is used somewhere. Okay. You know mu is used for what? Micro. Where did you see after that? Mu.
Friction.
Which one? Coefficient of friction. Where else did you see after that? You did it. Last chapters. I mean, not last chapter. Last semester's chapters. Statistics, yeah. Where else did you see? Come on. Start with P. Permeability. We use the same letter. Now we can also use it for refractive index. And mu is also used in nuclear physics. I mean, there's so many places they can use the letter. But when you actually like writing the letter, you simply look at the letter and say, all right, which chapter are you talking about? And then we know what it is.
I feel like there are plenty of letters and symbols out there. Why do they gotta use the same one for so many things?
Which ones? Like
mu, like why do they have to use mu for so many?
there are, but the mu is a convenient letter. That's what I think. There are so many letters. I mean, like alphabets in English, there are 26. So we are running. We can't use. Well, what is mu? Mu is a M. It's M in Greek. So we're just using the same thing now. Can you use M, actual M? No, we use for meters, we use for mass. we used it for so many things already, and then we don't want to get confused with the units and all that. So that's why, as a symbol for a quantity, mu is taken. But anyway, most books these days don't use mu, but they use N.
Wait, why do we use the Greek alphabet?
Because most...
More letters.
No, not because of that, because they're kind of unique, first of all. And some of the scientists, they were all like Greek, connected, Greece, like Greek scientists. And somehow, like the Greek alphabets and all that were, as you can see, the Greek alphabets are different. Although it sounds the same or means the same, and it's almost the same order. So alpha, beta, gamma, delta, So those are kind of epsilon, those are things. It's almost like A, B, C, D, E, so it becomes a little more easier to comprehend. It's not like strange. Well, definitely you don't want to use a Chinese symbol. Because it's pretty difficult to draw that stuff. So a symbol that is easy, see lambda. We already used it here. Lambda is a Greek. Theta is a Greek. You can see a lot of Greek right here. Theta is Greek. Lambda is Greek. Mu is Greek.
What about letters? It's like A and E, they're like right next to each other. It's like in like pronunciation.
Oh yeah.
They can use that or something. Instead of just using the same ones over and over.
Much harder to write, maybe. I don't know. It's like R or something like that. Yeah.
So that should just.
I don't know how, I mean, pronunciation itself is something that we need to look into. Go reading it. All right, come back. Refractive index is given by the symbol N. So now I'm going to write it again. Sine of theta A to sine of theta G is a constant ratio, which is VA to VG. Now, what is VA? What is the speed of light in air? Speed of light in air is 3 times 10 to the power of 8 meters per second. And the speed of light in glass is slower. 2 times 10 to the power of 8 meters per second. So what is VA to VG? 1.5. That 1.5 is what we call as the refractive index. That's the number. So refractive index doesn't have a unit because it's just a ratio of VA to VG. Okay? VA to VG. And VA is that, VG is this. So just 1.5. It's a constant number. But it is not for one material. It's not for one material alone. Look at this. It's a refractive index of glass with respect to air. So it's more important to know where is it coming from and where is it going to. So refractive index is for a pair of media. It's not for one medium. The term refractive index is for a pair of media. And so we write that one. So you can write all this down as well, but the most important focus is refractive index. Refractive index of glass with respect to air. So that's how we write it. This is this ratio, which is this. This ratio is equal to refractive index of glass. So the letter that you write here represents the letter to which it is going. Okay? Refractive index of this material glass with respect to air. Correct? Sometimes they also write like this, Ng. Now what does that Ng mean? Nothing is written here. When nothing is written here, it's nothing, which is vacuum. When nothing is written here, it refers to vacuum. Right? If it is just one letter without anything right here, it means this is referring to vacuum. So we can also write this as Ng divided by Na. We can write the same thing as Ng divided by Na. And what is it referring to here? Vacuum. And here also vacuum. But because vacuum and air are nearly the same, there's not much of a difference in speed of light. In vacuum to speed of light in air. Tiny difference, it is still there, but it's not so significant. And because of that, refractive index of air is 1. So if light is moving from vacuum to air, it's not going to be greatly changed. So if it is 3 times 10 power 8 in vacuum, when it enters air, it will be 2.9998, something like that. Okay? So it's slightly changed. So if I look at a ratio like that, it is nearly 1. So we take the refractive index of air as 1. What's the refractive index of vacuum? 1. You know? If it's moving from vacuum to vacuum, no change. So if there's no change in the speeds, that's 1. And here, refractive index of glass with respect to vacuum is almost the same as air, so it's 1.5. You saw that. So when you say 1.5 is the refractive index of glass, we are always referring to either vacuum or air. Make sense? Now, when you put this equation and that equation together, sine theta A over sine theta G is equal to Ng over Na. I'm putting them together like that. Although this is how they write it, but you can always split it up like that. Cross multiply. When you cross multiply, you see it becomes Na sine theta A is equal to Ng sine theta G. When you cross multiply that equation, you get this. Which means the product of the refractive index of this medium and the sine of the angle here in this medium is equal to the product of refractive index in this medium times sine of the angle here. Make sense? So the product of refractive index and the sine of the corresponding angle of incidence should be equal to the refractive index of the next medium times sine of the angle in that next medium. And suppose it's going from here to another medium like oil. Still, the ratio is always going to be held, right? So simplifying this whole thing, we can write when waves or rays are moving from one medium to another medium, since the product of these two are always going to be the same, no matter what medium it's going to, n sine theta in general should be a constant. Well, this is the ultimate equation. But remember, what is n? N is a refractive index of the medium you're talking about. And here n will be the refractive index of this medium. Okay? And this is called Snell's law. Snell's law. When waves go from one medium to another medium, there's always a constant ratio that is held. And that constant ratio is called the Snell's law. Questions here? Some of the stuff that you should know as a logic information is this. This is air, which is rarer, and that is denser, which is, say, glass. That's a normal. If a ray comes and strikes like that, which way will it bend? Will it go straight like that? Which way will it bend?
Down.
So think of the wheel and axle. Think of this as a wheel and axle. And it bends that way, right? So it's going towards the normal. It's going, the ray bends towards the normal. So simple as this. When anything is going from rarer to denser medium, then the ray or the waves will bend towards the normal. And opposite is also true. Denser to rarer. If it's going from denser medium to rarer medium, which way will it bend? Away from the normal. Away. You can say that this angle is bigger. So it's supposed to have gone straight, but it went that way. Supposed to have gone straight, but it bends that way. Okay? So this one bends towards the normal. This one bends away from the normal. Make sense? So you can use your logic that way. If it's moving from denser to rarer, this is what happens. If it's moving from rarer to denser, that's what's supposed to happen. So if your calculations are not matching up, then you can work according to that. So let's do a problem on this, a quick problem. If this is glass, and the refractive index of glass is 1.5, and if there is water here, and the refractive index of water is 1.33, which is approximately the number. And you know, when you say refractive index, we are talking about refractive index for a material for a particular color. Not for all colors. This number is not for all colors. It's for an average color, which is, what's the average color of white light? What's the middle? Like, you know, light, violet, red. Violet is like 400 nanometers. Red is 750 nanometers. So an average color is yellow. Yeah. And the average, the yellow part of it is approximately 589 nanometers. That's basically what it is. Yellow's color, yellow's wavelength is 589 nanometers. So when you're looking at something that's burning, you know, if there's some fire that you see there, most probably you'll end up seeing yellow color. Right? Like a candle flame. You look at a candle flame, you normally end up seeing what color? Yellow. It's got a yellowish tint. But close to the wick, that's a place where it is super hot. Right? What is the color? Blue. Right next to the wick is blue. Even closer than that is like blank. Why is it blank? Ultraviolet. You don't see it, but that is there. It's burning. Even though it's burning, the wick will be seen clearly separated from the flame. Have you noticed it? The wick is actually clearly separated from the flame is separated. Now, why is it separated? Because you are actually seeing a little part of the ultraviolet right in the middle. And then comes a blue. And then to the average color. And towards the end of the flame, it will be more orangish color. So yellow color is, so this wave, this refractive index number that is quoted is for that yellow color. So it changes from color to color. Okay? So just keep that in mind. So suppose you have a ray coming in at an angle of 30 degrees here. What is supposed to happen on this side? What is the angle? You can do the calculation. What you are going to use is a Snell's law. So tell me which way it's going to bend. Away from the normal. Yeah, that's your expectation. Yeah, because this is going from denser to rarer. It is expected to go like that. That means you're expecting a larger answer. Okay? So you use Snell's law. Ng times sine of the angle here. Or you can just write N1 sine theta 1 is equal to N2 sine theta 2. Calling this medium as 1 and that is 2. So N1 1.5 sine 30. Make sure your calculator is in the degree mode. N2 1.33 times sine theta 2. So what is the angle theta 2? 34 degrees. So that means it is not going straight, it's bending away from the normal like that. And that is 34 degrees. You can see that very clearly. So you can exactly calculate how much is the angle. So we are just using Snell's law blindly. Just N1 sine theta 1 is equal to N2 sine theta 2 for those two. Now what if it comes back? Suppose this is water, and suppose the water finishes there, and back to glass. What will happen? It will come back, bend towards normal. It will come back. Got it? I'll show you that quickly. This is see, this is like a convex lens. Yeah, you can see that light is coming out from there. It's like a, see? What is this material? This is perspex. This is what you're wearing right now. What you're wearing is perspex, this material. Okay? It's very close to glass. The refractive index of this is nearly glass. That's why they use for lenses. So perspex, this is perspex. So I'm going to send light into this. If you can just turn off the turn off that light. Operator for you. All right. So if I'm going to keep this block like this and send the light straight down into it, do you see any bending? Nothing at all, right? It just goes straight through. What if the angle is oblique? You see the bending here? Can you see reflection?
Yeah.
Can you see two reflections?
Yeah.
That's the multiple reflection I told you about earlier. Okay. So you can see it's bending inside and then coming back out. It's something like this. Like that.
Straightens back
Okay? Turn the. And what we'll extend this to, later on we'll extend this to prisms and then lenses, and that's how we go on, right?